Have you ever just looked up at the night sky and really thought about the absolute silence staring back down at you? I mean, we live on this tiny, fragile world that is absolutely brimming with life, color, and noise. Yet, right beyond our thin atmosphere lies a cosmic expanse that is, with almost offensive consistency, nothing but dead rock, frozen gas, and radiation-soaked silence. It's an emptiness so profound it can literally make you ache. We've spent centuries building massive telescopes and launching probes, desperately hoping to find just a whisper of a neighbor. But what we find, time and time again, is silence.
It brings us to a mind-bending, existential question that most standard textbooks completely ignore. If life is so precious, if it's the ultimate, crowning achievement of chemistry and physics, why does the universe seem almost completely empty? But what scientists are beginning to discover is something far stranger than a universe that just somehow failed to create more life. This emptiness we observe, it isn't a failure at all. It is a deeply terrifying yet incredibly beautiful mathematical feature. Okay, let's dive into this. To truly grasp this mystery, we first have to comprehend the sheer, terrifying scale we are dealing with here. By current estimates, the universe has built at least 2 trillion galaxies. 2 trillion. And each of those galaxies contains hundreds of billions of stars. Basically, the universe has populated almost all of this incomprehensible expanse with worlds that are utterly, magnificently lifeless. Trillions of dead, silent arenas.
And then, against that sprawling, infinite backdrop of 2 trillion galaxies, we have this number, 1. Just 1. As far as we can currently confirm, there is exactly 1 pale blue dot out there with anything moving on it. The contrast induces a kind of cosmic vertigo, doesn't it? Either we are a miracle so wildly improbable it strains the very definition of the word, or this vast emptiness is doing something absolutely vital that we just haven't figured out yet.
Think about it like this. Imagine you dump a bag of 200 different colored marbles all over your kitchen floor. You easily find 199 of them scattered around in plain sight. But the last one, the 200th marble, which happens to be the only one that actually matters, is wedged in the single most unlikely gap between the dishwasher and the wall. We are that one marble that ended up in the gap. But the real question is, if all you needed was one marble with life on it, why did the universe build such an impossibly large, extravagant kitchen floor just to hide it? Why the sheer wastefulness of space?
Now, if you open up any standard introductory astronomy textbook, you'll find a nice, comfortable answer to this called the rare earth hypothesis. It basically says that complex life requires a freakishly specific checklist. You need liquid water, the perfect temperature, a stable magnetic field, and a massive neighbor like Jupiter to vacuum up asteroids before they sterilize your planet. The textbook basically shrugs and says, well, most planets don't hit the checklist, so most planets stay dead. But honestly, that only explains how rare life is. It completely ignores why the universe is so extravagantly, almost deliberately large in the first place.
Because if we're just this wildly improbable roll of the dice, why are there so many dice? To answer that, we have to look at the hard physics of how we actually got here. In the very first microsecond of existence, protons and neutrons fused. By the first second, the entire universe's density had to balance perfectly. And then, it took 13.8 billion years for chemistry to slowly, painstakingly assemble itself into biology. The textbooks skip the real mystery here. Why are these massive, sprawling timelines and incredibly vast dead spaces actually required for you to even exist?
Which brings us to a massive revelation, and honestly, one that will probably change how you look at the night sky forever. The billions of dead, barren rocks aren't just background filler, while the universe got on with the real work of making life. The emptiness is a requirement. You literally cannot have life without the billions of dead planets. They are an absolute necessity.
To understand why, we need to talk about dark energy. Back in 1998, astronomers made this Nobel Prize-winning discovery. They realized the universe's expansion wasn't slowing down due to gravity like everyone thought. It was actually accelerating. And this is driven by an unseen force we call dark energy. It turns out the vast, supposedly empty space between galaxies, well, it isn't passive at all. It holds an unimaginably precise energy that dictates the physical tension of all reality.
The value of this dark energy, known as the cosmological constant, is staggeringly small. I mean, we're talking about a number so tiny it's almost impossible to picture in your head. It has 120 zeros after the decimal point before you even hit a 1.
If this number were slightly larger, even by a fraction of a fraction, matter would have scattered so incredibly fast after the Big Bang that stars and planets could never have formed. But if it were slightly smaller, the entire universe would have just collapsed back in on itself within the very first second.
Let's play God for a second with a thought experiment we can call the builder's dilemma. Imagine you try to build a smaller, much more efficient universe. Let's say just one galaxy, a few stars, no wasted space. What happens? Well, immediately the background energy density changes. Gravity dynamics alter. The universe either cools too fast or too slow. Those stable, long-burning stars like our Sun completely fail to form. Physics collapses entirely. Every single time you try to strip away the dead distance and the sterile light years, you break the universe. Life and emptiness are an inseparable package.
And this brilliantly illustrates the reality of our cosmos if we compare it to baking bread. Think about it. If you want a beautifully airy loaf of bread to rise, you need yeast to produce tiny gas bubbles inside the dough. Now, the yeast doesn't just target the final loaf, it fills all the dough uniformly, but only a tiny fraction becomes the perfect bubbles. Life is the bubbles. The universe, the trillions of dead planets, the barren moons, the sterile light years, that is the bread. You just cannot get the rare bubbles of life without the vast dead medium holding the whole shebang together.
This insane precision appears everywhere you look, which just deepens the mystery. Take what physicists call the flatness problem. The observable universe's total energy density sits almost exactly at a specific critical value, which they denote as omega. Right now, omega is roughly 1.002. Essentially, it's exactly 1. For it to be this close to 1 today, nearly 14 billion years later, it must have been calibrated with absolute surgical precision at the exact moment of the Big Bang.
In that very first fraction of a second of existence, the margin of error was less than 1 part in 10 to the power of 60. To put that completely incomprehensible number into human terms, that level of precision is equivalent to weighing the entire planet Earth and being off by less than a single atom. Without that exact, mind-blowing flatness, you just don't get the billions of years of stable expansion needed for chemistry and biology to evolve.
Let's shift our perspective for a minute and see how this plays out across different scales. Look inside a single hydrogen atom. It is more than 99.9999% empty space. If you took all the atoms in your own human body right now and removed the empty space, it's absolutely staggering. Your physical matter would condense to 1/1000th the width of a single human hair. And what about out in our solar system? Everything that isn't the sun, every planet, moon, and asteroid combined makes up less than 0.2% of the mass. Emptiness literally is the structural scaffold of reality itself.
Zooming out to a cosmic scale, the average density of the universe is roughly 6 hydrogen atoms per cubic meter. The absolute best, most pristine, high-tech vacuums we can manufacture in laboratories right here on Earth still contain millions of atoms per cubic meter. The universe is emptier than anything we can even dream of creating. Yet, if you removed this dead space, if you somehow compressed that quantum vacuum between the electron and the nucleus, chemistry itself would instantly collapse.
So, this all leads us to a profound philosophical shift known as the anthropic principle. At its core, it states that the universe we observe must be compatible with the existence of observers. But it goes way deeper than just saying we got lucky. It means the universe didn't just stumble upon life. The very laws of physics, the cosmological constant, the gravitational force, the mass of an electron, are so finely calibrated that they literally require a universe of exactly this vast shape, size, and emptiness to work.
So, the crucial point is this: those empty planets aren't a failure. They are the physical signature that the universe had enough time, space, and material to run the lottery of life. As the saying goes, every dead world is a ticket that didn't win. The billions upon billions of silent, barren planets out there aren't a tragic waste of space. They are the absolute proof that the cosmic lottery ran long enough and on a grand enough scale for you to be sitting here today. You are not proof that the universe is generous, you are proof that it is unbelievably precise.
As we wrap up this explainer, I want to leave you with a thought that really lingers. The universe operates on rules we are only just beginning to decipher, utilizing an emptiness so vast it literally holds reality itself together. Perhaps the greatest mystery isn't why the universe contains billions of empty planets. Perhaps the real mystery is why one of them became alive. So, what do you think? Are we truly alone in this perfectly calibrated cosmos? Drop your thoughts in the comments below.
And hey, if this journey shifted how you see the night sky, please like and subscribe to join the discussion. Until next time, keep wondering.